Good morning. Good morning, everyone. My name is Olive, and I am a PhD student in Biomag. And today we will be talking about this paper called Discovering Network Dynamics with Neural Symbolic Regression from Nature Computational Science. So as usual, we start with reading the abstract first.
네, 앉으셔도 돼요.
So is everyone finished?
Yeah.
So can you tell me what the gap sentence is?
Despite the explanation is
Yeah, so it is the second sentence. Despite the accumulation of observational data across many domains, mathematical models exist in only a few areas with clear underlying principles. Do you have any opinion about this abstract?
but I think the gap is just for instance like something like general gap sentences about the simulation, not just the specific one.
Yeah, I agree. So the gap here is more of a general gap in all research that involves symbolic regression. So maybe while we are talking about the paper, we will see a more specific gap. So first, we will be talking about a neural symbolic regression, but for those who are unfamiliar, let's introduce what symbolic regression is first, briefly. Let's say we have some input data from three variables, x1, x2, x3, and we have their corresponding output values 1. And we know that these inputs and outputs are related by a function f, which we don't know the form of. So what symbolic regression does is that it takes in the input and output values, and it tries to infer what the form of the underlying equation is. So if we put these values into the symbolic regression algorithm, it should give us an explicit formula. So this is good as compared to the other machine learning approaches, because here we actually have an expression of the formula. And to build this formula, what symbolic regression does is it combines inputs like variables, operations, and constants to build the final formula. So for instance, one formula can be represented as a tree. So this one is just x1 plus x2 plus x3. And we can build some other candidates in the same way. So we call this, so this is the initialization of the symbolic regression, and this is generation 1. After creating the candidate functions, then we check it against the data that we have and then compute the error. And for those that have the big error, we just discard those candidates. And then for those who have lower errors, we evolve this these candidates. And the way that we evolve these formulas are by genetic programming operators. One example is crossover. So what crossover does is it selects two components of two candidate functions and it merges them into one like this to produce another candidate function. And one more way to produce another candidate function is by mutation. So what mutation does is it just selects a small part of the candidate function and it varies it randomly. So here the multiplication is replaced by addition. So these crossover and mutation operations are called genetic programming operators. And we call this the generation 2. And then again, we compute the error against the data and discard those with high error and evolve those with lower error. We continue this until convergence or a stopping criterion. So eventually, this is iteratively applied until we obtain a final formula that maybe looks like this. And if we compare it to the actual true function, it's supposed to be a good approximation. So symbolic regression works very well for very simple functions. However, in real systems, we deal with more complicated equations. So what if we have this kind of network? So in this system, we have 236 nodes and 320 edges. And the underlying function or the function that we want to discover is something looks like this, where the X are the node states and A is how each node is related with each other.
So in this example, you can see the coefficient table here. Yeah. Is there any another some algorithm to determine coefficient or parameter value?
You mean the
Yeah. So in the previous, you mentioned crossover and coefficient value. It seems that the parameter value cannot be obtained only from that.
I think there is another genetic operator, but I failed to put it here.
For each generation, we discard some bad performance possibilities and for survival one, we also several operation. For example, you suggested mutation or something like that.
Yes.
I wonder that so mutation, for example, mutation for survival one is always better than the previous discarded one.
I think not, because the mutation, I mean the way that mutation happens is that it randomly changes a particular node and it doesn't have any basis for that mutation. It is random. So it could be worse than the previous one. And if it's worse, then we just discard it in the next step.
So this optimization is quite heuristic. So we cannot sure whether it risks the good.
Yeah. So then for a bigger and more complicated network, if we perform the usual approach, then it becomes really inefficient because we have too many nodes and too many edges. So in this paper, one key idea is to use the network structure. So we are given the network structure in order to make the algorithm faster. So instead of representing the variables by x1, x2, and x3, we use the network connections that are given to us by defining some things that they call the network dynamic operators. The first one is the source mapping. So here we just map x to all the source nodes, so where the influence is coming from. So if you check each edge here, what one source is x dot, and for the second edge it is x2, and then the last source is x3. And at the same time, we also define target mapping. So it is just the opposite of the source mapping. We just map x to all the target nodes. And finally, we have the aggregation mapping. So for each node, we just summarize which edges are going into that node. So for x0 here, we have E2 and E3. And for x1, only E1 is going into that. And then for x2 and x3, there are no edges going into them, so they are just 0. So basically what these mappings do is just summarize how the nodes are connected with each other. So in this way, the search space reduces. So for example, here, if this is our target equation, we compare the search space when there are no network operators and when there are network operators. So here, without the network operators, the inputs are the individual nodes, individual constants, and elements in the connectivity matrix, and operations in the functions. So in this particular case, the size of the symbol set is 3n plus 3. And then if this is the target equation, the length of this, in this case, is 6n plus 1. So for each location in the formula, we have 3n plus 3 candidate symbols. So it is growing in this way. So 3n plus 3 to the 6n plus 1. But with network operators, what we do is just we add as inputs the network operators that were defined previously. And for the variables, they are inputted as vectors instead of individual inputs. So that this will become the target formula. And here, the size is 8 and the length is 9. So that the growth of the search space is just 8 to the 9. And we can notice here that for the case with the network operators, the growth does not depend on the number of nodes. So just the size of the symbol set and the length of the target equation.
But it should be vector function.
Which one?
Rho.
Yeah. So it's just also, it functions also just as a just a normal function, so like sine or cosine or whatever.
So I mean, for each coordinate of the vector value function, they have all the independency. So it would increase the degree of freedom.
Again?
So the function rho
Mm-hmm.
is that have, for example, if the x is n-dimensional vector, so it should also be n-dimensional vector.
Mm.
So it will so at each coordinate of the function
Okay.
can be independent.
I see. I think, yeah, maybe one thing that they assumed here is that the connectivity between the nodes are like governed by the same rho. But later on, they address the case where each equation has a different function.
Okay.
Okay, so first they use the network operators, but still maybe the search process can be reduced. And this is where they introduce their main method, which is ND squared, or neural discovery of network dynamics. And the general idea behind this process is that the input is the network structure and the time series of all nodes. And it is inputted into an ND former, which is a neural network. We will talk about that later. And the role of the ND former is to guide Monte Carlo research. And this research is the search algorithm for the symbolic regression that we will show here. And at the same time, the tree search is feeding some incomplete formulas to the ND former. And so the ND former, based on the incomplete formula, will guide the search again so that it gets a candidate complete formula. And based on the complete formula, some reward is computed. And the way that the reward is computed is by comparing the output with the actual data. So the reward is just based on how accurate the formula is compared to the data. And so the reward is fed back into the tree search. So there's a lot going on in this algorithm, but we will discuss them one by one. So how do each of these components work together? Let's talk about the Monte Carlo tree search first. So it is quite different from genetic programming. So in the nodes in this tree search, you can actually put some placeholders. So the initialization is just a placeholder, so there is nothing there. And then the next step is to select what to put in that placeholder. So for example, we have 4 candidate actions, they call them actions. So the action is replacing that placeholder with, let's say, X or row or some other function. And the way we select the some more likely choices is by this equation. And it depends on these 3 values. So N is just the visit count of the action, if you actually use that action. And then Q is the best reward so far. So this is just the initial step, so there is no reward yet. And then pi is the probability of choosing the action at a particular node. But that probability is provided by the ND former that we will show later. So, and yeah, the summation part there is the sum of node visits also for different actions. So let's say these are the 3 selected ones from those candidate functions. And what the ND former does is it predicts what symbol is most likely to be matching with the data. So it gives us some probability values. And let's say the sign function is 0.6. So probably the data shows some oscillatory behavior. Then after this expansion step, we do some simulation. And what happens in the simulation is we input these candidate functions, and then we sample the next symbol. So what I mean by this one is, for example, this candidate action, if we fill up this part with raw, we are sampling the next symbol. And another example is here. If we fill this up with X here, we are sampling the next symbol. And we do this until the formula is complete. By complete, I mean that there are no more placeholders. So if it is not, then you put it back to the ND former until you have a final formula. And then if you get a formula, the reward is calculated. So it's compared with the actual data. And you have some reward values per candidate function. So I just put here 2 for each, but you have to do this multiple times. And then you just get the maximum reward value here. So you run this multiple times per node. And then after simulating all the samples, we perform back propagation. And for this one, we just update the number of visits here. So you can see that we only backpropagate this 3 candidates that were chosen, and X is not visited. And we also update the rewards. So the initial reward was 0 because there was no reward first, and then just compare it with the maximum reward. So after the backpropagation, we have an updated search tree with each path having their corresponding n values, number of visits, and the corresponding rewards. And this updated search tree will go through the whole process again. So to illustrate, I will just also show the iteration 2. So iteration 2 has this tree already with corresponding n and q values. And then now some candidate actions will be suggested again, but we will choose only, let's say, the top k. Here it's k equals 3. That has the maximum value u there. So it is dependent on the number of the visits and the rewards so far. So after selection, you will notice in this step that the search becomes more biased towards the more promising formulas. And then for the selected ones, we perform the expansion again so that we get the probabilities of each action, and then perform simulation again by sampling each candidate next symbol, perform the backpropagation again. So we only compute this for the path that we initially selected. So we add the visits and we update the best reward so far. Then finally, we update the search tree again.
Here is the action space is fixed, or is it generated by something like the ND former?
The action space, actually, I think from what I understand, they just fix all the symbol set and then select from there.
I see.
So this is how the tree search works. So it is performed iteratively. But now, now that we know how the tree search works, we want to know how the ND former guides the search.
So by the selection stage, so you mentioned some node visits. So could you explain more about that?
So the node visits is like just how many times it is visited through the backpropagation. So for example, this grows more, right?
Yeah.
So let's say this is like maybe 5 levels. And then for each iteration, this path is always visited. So it is just adding the number of times the algorithm chooses to pass through that node.
In the initial iteration, we don't care about that.
In the initial iteration, there is no node visit yet. So it is just updated in this.
And it somehow choose only at the initial iteration. It somehow choose only 3 candidates. Is it just a random choose?
So it still depends. So in the initial one, there is no number of visits and there is no rewards, but we have the probability.
I see.
So in the initial iteration, it only depends on the probability of choosing that action based on the data. But I chose here k equals 3 to make it simpler, but usually it's like a bigger k because the network is very complex.
Here, what is S and A?
So here, S is the node and A is the action. So N is like the number of visits given an action and the node.
And the simulation stage, we sample X symbol. Why should we do? So I didn't get.
I think because eventually we will have a complete formula.
I see.
So it depends on that reward. So for example, this one is already a complete formula. And then the reward that you get from this will be the basis on whether it represents the data.
So reward can be calculated only for the full
Yes.
equation, so that we need to anyhow we need to sample more next steps to complete the equation.
So while it is incomplete, we have to do this.
Just naive question, but is it always does it always go to the complete state within a finite step, or
Sorry?
so is this algorithm always goes to the finite always goes to the complete state within a finite steps?
No. So I will show later, but basically in their algorithm, they set a fixed number of time steps. And after those time steps, there are nodes that are complete and that are not complete. So we just look at those that are completed.
Then we just discard
Yes.
the incomplete one.
Yeah, so now we want to discover how the ND former guides the search. But the idea behind the ND former is that it is a next equation token predictor that is based on the data and the structure that it receives. So it functions like a large language model. So for example, if you type something on ChatGPT, it predicts the maybe top 5 possible next words. And the ND former functions in the same way. So here, for the ND former, you feed it the network structure, the time series, and the incomplete formula. And if you put it through the ND former, it gives you some candidate next formulas and with their corresponding probabilities, as I showed earlier. And in a bit more detailed way, this is how the ND former is structured. So first, the structure and the time series are inputted into a graph neural network. And what it does is it just learns the information from one node to its neighbors. So it outputs some embedding of node. For example, H1, it is the embedding of node 1 with its neighbors. And then this embedding is, so it's like a local context because it focuses on each node. And then it is inputted into an encoder, which then creates a new embedding, let's say H1 prime and so on. But this is the embedding of each HI prime with all the other H. So this is like the global context. So initially in the GNN, it just like encodes the properties of one node with its neighbors. And here, it encodes the relationship of one node with the rest of all the nodes based on the input from the GNN. And so basically this step just embeds the data. And at the same time, the incomplete formula is fed into an embedder. So that it just creates an embedding for the incomplete formula. So now we have two outputs that will be fed into the decoder. So what the decoder does is, based on the context that it gets from here, and based on this embedding of the formula, it predicts what should fill up the placeholder. So this decoder is fed into an MLP, which converts, it maps the decoder output to some score for each next symbol. And then the MLP outputs the policy, or this is just equivalent to the probability distribution over the possible next symbols. So this is how the probability for each action is computed. Okay. Yeah, and the reason that the ND former performs quite well with guiding the tree search is because it has been trained on 1 million synthetic dynamical systems. So they try to generate like 1 million networks with their corresponding 1 million sets of time series and the corresponding ground truth formulas. So they fed it into they pre-trained the ND former to learn the patterns from this information. And basically the pre-training step works something like this. So we have the ground truth formula like this. And this formula is split into something like training and testing sets, but it is split in this way. So the first split is the partial equation. So you just kind of hide this one. And then the label will be the actual answer. So you feed this partial equation into the ND former, and you make the ND former guess what should be here. So then the ND former will have something like this. So it has several candidate symbols, and it gives us the probability. So basically, the goal of the pre-training is to learn the parameters of the whole model that will assign a higher probability to the correct answer. So yeah, basically, it learns the pattern of the dynamics so that it can guide the symbolic search more efficiently.
So when they trained this model, did they add some noises in the time source data, or they used pure time source?
I'm not sure. I'm not sure, but they only mentioned that it's 1 million synthetic data sets.
And should it be some regularly sampled time series data, or so is there any restriction for format of time series data?
I think I didn't check that detail, but okay, so now finally we know how the tree search works and how the ND former helps it. So after the termination, in this case, their stopping criterion was a specific number of iterations. Eventually, we will have some tree that looks like this. And this was related to the question before. So you can see that some of the final nodes are incomplete, like the phi s of something there. But we only check the terminal nodes. So when we say terminal nodes, those are the formulas that are complete. We check the terminal nodes, and so for each formula, there is a corresponding length of the formula and the error. And they didn't really put much detail into this, but they said that we only keep the formulas that are not dominated in length and error. So basically, if the formula is too long and the error is bigger than the rest, they are discarded from the set of candidate formulas. And after discarding those formulas, these are the remaining formulas are what they call the Pareto front, or these are the formulas with the best trade-offs between the simplicity and the accuracy of the formula. And since there are many formulas, so the last step is like selection by an expert. Because I think
they did not just a single optimal solution.
No, so that is
Only for the
part
Pareto
that-
plots.
So there are like several candidate solutions, but the final one will be selected by the user. So yeah, so that's how the ND squared works. So they applied it to several systems. This is the first one they applied it to. So this is like the simulated Rosler system. And yeah, basically for this simulated system, it was able to recover the underlying correct formulas. Exactly, so the R squared is 1. So I think that's because it's purely simulated data without noise. And then they also showed that if we remove the N deformer, so it's simply, I think if by removing N deformer, it's just the Monte Carlo tree search. If we remove that, then the performance of the whole ND squared reduces by a lot. So here, the bar represents the mean R squared, and the numbers here is like the number of equations that were exactly and correctly inferred. So here it's 3 out of 3, and for the ND squared without the N deformer, so the mean R squared is still high, but even though the error is, even though the R squared is high, I think 0 out of 3 means that the discovered formula is not exactly the ground truth. And similarly here, let's look at this line and this line. So this is the simulation time for the ND squared for the Michaelis-Menten system. So it is way faster than this line, which is the one without the ND volume. So it takes much longer. And they also showed how it speeds up compared to the case where there is no ND volume. So the speed is much, much faster compared when you don't use the ND format.
How do we measure error? Formula is X and the result is 1.01x.
I'm not really sure how much error they allowed. Sorry, it is. I think it's all in the supplementary file, but it's like 72 pages. But I guess they would allow some small error for that. So like when it's X versus 1.001x, I think it could be considered as correctly incorrect. And then they also claim that they recover equations that are different from existing models that model that like true data. So for example, here this is the system for the yeast cell cycle, and the existing formula is the one above there, and the one discovered by the ND squared is the one below. They show that it fits the data very well, and it reduces the error by at least 50%. But since we don't know the actual correct underlying formula, we just base their accuracy on the error between the formula and the actual data.
So ground truth is the most predicted by existing real time.
We don't have a ground truth, but for this system, like what they say is that usually for the yeast cell cycle, they use this model to model dynamics, but they claim that they have recovered a better equation that fits the data better than the existing one.
I might have missed, but
Hmm.
we need to specify the structure of network.
In the explanation of the method, they said that the structure should be an input. But actually, for this particular example, so they don't know the network structure. So they assume that everything is it's like a fully connected network, but they let the algorithm decide the weights. So they also explore other cases where, for example, there is no network structure.
Did they also get success to recover that existing formula, or did they just put that their formula is better than?
I think they just claim that their formula is like lowers the error compared to the existing formula.
I think there is threshold of the time variable. So is it possible to extrapolate the time variables that they can expect more than just for example, there's 100 times. It's possible they can expect more than the time threshold. So
You mean if the data is longer than this?
yes. So is it there a blow up or it dies to the zero? Is there any explanation about that?
I don't think they really specified how long the time series will be.
Oh, okay. Maybe similar question. So
Hmm.
when they test the RBC,
Mhm.
evaluate it, did they split it, the time series into training and testing?
They did that, but they also did the part where they don't you mean like for prediction or?
And for prediction of the equation, they need to use the time system.
Hmm.
Then an evaluation is tied to the training endpoints or other test times.
Okay. For this example, they only computed the error between the formula output and the actual data. But for another example, they split it into train and test. So particularly this example. So this one is an epidemic transmission dynamics model across different locations and different scales. And basically, yeah, they obtain specific formulas for each location, and these are the corresponding R-squared, and you can see that it matches the data quite well. And they also mentioned that this accuracy generalized to like unseen periods. So this is when they split the data into training and test splits, and then they test it with the test data. Yeah, so actually, that's everything. So the ND squared is just uses a learned model to guide the research for the symbolic regression, and it does not use the usual genetic programming and replace it with the MCQS. And finally, the accuracy is quite high because it was pre-trained on the large scale synthetic data set. So I think these are the main take home messages from the